So the conclusions from our discussion last hour were that for an alkyl halide, some of the LUMO is on the adjacent beta carbon. And just to reiterate, I was showing you some of this stuff about, mixing the sigma with the sigma star together in both plus and minus combinations to give you an idea of how to get to what the LUMO actually looks like if you do a calculation. But really, the stuff here, which I will just sort of circle and then gray out, is not that essential in the sense that I'm actually not going to gray it out, that's taking too long. All you need to know is that when a filled orbital lines up with an empty orbital, that the electrons in the filled orbital spread out towards the empty orbital, and the empty orbital spreads out reciprocally towards the filled orbital. So some of the LUMO is going to be on the beta hydrogen. Okay, and that's all you need to know. Go ahead. No. Any other questions? I'm just kidding. Asked me to move my mouse. Sorry. Yeah, no. Okay. So what this means now is that a nucleophile that encounters an alkyl halide may have to decide whether to attack the LUMO at the beta hydrogens, or at the carbon. Now, what I'm going to do now is just fill in the other beta hydrogen on that methyl group. There's another one here that can line up with the empty sigma star. So what you're seeing here is the actual LUMO. You get that from the carbon iodide sigma star with sigma CH to sigma star hyperconjugation. And what we're seeing is that those hydrogens on the beta carbons, and I guess there's two of them, so we could call this one beta 1 and this one beta 2, have some LUMO on them. All right. So I'm emphasizing this because the consequences of the reaction are different depending on whether the nucleophile attacks at the carbon or at the hydrogens. So if the nucleophile attacks at the carbon, that's exactly what we've done previously. The product of that is the substitution product, and you get inversion of stereochemical configuration. However, if the nucleophile instead attacks at the hydrogen, it turns out, and the consequences of this may not follow directly from our talking about bonding or anti-bonding orbitals, but if you attack the hydrogen, the electrons in the carbon-hydrogen bond move over, dump themselves completely into the sigma star, and the leaving group leaves. The product then is not a substitution product, but an elimination product. And it's called an elimination product because you've removed a hydrogen from the molecule and your leaving group I- left. Okay? So right from the beginning, and your text actually deals with substitution, which Sn2, and then elimination. Your text actually deals with this in separate chapters with the idea that they're going to teach you about substitution first, they're going to teach you about elimination, though it's a separate thing, and then only at the very end are they going to pull back the curtain and say, these were competing with each other all along and you didn't know it. And then they're going to expect you to go back and reorganize all of your information and be able to predict when it's going to be substitution versus elimination. I've taken a different approach since I've been teaching this class. I want you to know that from the beginning so that it's less surprising later on. Because this reaction, and we'll learn about this more specifically later, but this reaction also is concerted, also goes through a single transition state. Also, the rate law involves both the nucleophile and the electrophile. So we're going to call this an E2, or a bimolecular elimination reaction. And the product is an alkene. Now, something that I'm not going to talk about yet is that there was another stereoisomer possible. There was also another isomer possible in which we could have removed the other beta proton. I'm not showing you all the possible elimination products, and we're going to deal with those complexities later. But I want you to see at an early stage that these two things compete with each other. Yeah?
So the reason the iodide breaks off is because the pi bond is formed?
Yeah, the reason the iodide breaks off, conceptually, if you want to think about it this way, we remove the proton, the electrons that would be left behind in the conjugate base jump over and attack the sigma star, making a new pi bond, and because you're filling a sigma star, the leaving group leaves. Yeah?
So why is the orbitals of the H of the protons and the anti-orbital, why are they different colors?
They're different colors because I'm just drawing the LUMO, and that comes from the minus combination. So don't get too hung up over the difference in colors. I'm drawing them to be accurate with what the LUMO looks like. But as I said, in an elimination reaction, you remove the proton. If you stop there, it would just be the conjugate base negatively charged here. But those electrons are adjacent to an antibonding orbital. If they dump into it and form a pi bond, the leaving group leaves. All right, that's an elimination reaction. Okay, so we are going to talk about what what characteristics in both the electrophile and the nucleophile that favor elimination versus substitution. Now, are there anything else you want to ask about Sn2 reaction mechanism at this stage? Yeah.
I just want to ask something about the thing down.
Yeah.
Where it attacks the hydrogen.
Yeah.
So the nucleophile attacks at the hydrogen, hits the hydrogen, and the electrons that are in that bond, they just go into the anti-bonding orbital, which takes the I off.
Yes.
Okay. And then they find their way to the pi bond.
You could say that electrons in the CH bond mix with the sigma star. I don't know what the best way to say that is, but we get a new pi bond and a new pi star. And if we stop there, we'd have too many bonds to carbon, so iodide leaves. So those three things happen in a concerted way at the same time. Yeah?
Maybe you'll explain this, but why don't the electrons just stay on the carbon to make a carbon ion?
Right. So the question, yeah, it's a great question. The question is, why don't we just remove the proton? I'm getting somewhat confused with stereochemistry, so I'm going to stop drawing it for our purposes here. Yeah, the question is, why doesn't the nucleophile just remove the proton, and then you get what's called the conjugate base. And then at that stage, can the electrons kick over, make a pi bond, and the leaving group can leave to give you the alkene? And the answer is that's a really great proposal, and actually there are reactions that go that way. Technically, this mechanism is going to be called E1CB. It's a E1 reaction because it's unimolecular. The deprotonation step is presumably fast. Wait, I forget. nope. This is the fast step, and then this is the slow step. So there's only one molecule involved in the slow step. And things that would favor this mechanism would be anything that stabilizes a negative charge. You're going to see reactions in 352 that go by this mechanism. I don't know how much we'll encounter that in 351. All right. So that was interesting, but lest anybody think they need to know it or memorize it at this stage, I'm going to shrink it down and put it there and say a curiosity to not worry about. Okay. Anything else? Yeah.
So we're saying that it can do elimination or substitution on the same molecule.
Yes.
Is one of them significantly more likely or more stable than the other?
Is one of the options significantly more likely than the other? We're going to see that the answer to that question will depend on the identity of the alkyl halide and the nucleophile. That makes sense because the rate law for both of these reactions involves both the nucleophile and the alkyl halide. So, yeah, we're going to see that there are things that promote one versus the other, and we'll talk about all of that. Probably not just yet. Okay, what else? Yeah.
How do we know that it does attack that hydrogen and not just the other one on the top there?
Why couldn't it attack the other one on the top? It totally could, and if you did, you would get this product. And you could also get the cis product. And we will talk about, it turns out the trans product is major in this case. We'll talk about why that is. Has to do with alkene stability. All right, what else?
So
Yeah.
Just to clarify, so we're talking about the second possibility where instead of attacking the antibonding on the carbon iodine, it attacks the hydrogen instead.
Yeah.
One. Okay.
Yep, elimination is if we attack if we attack the LUMO at the beta hydrogen. Okay, so right away from the beginning, because you know what the LUMO looks like, you're aware of this possibility for two other reactions. That way, two different reaction consequences. That way, when we go tell you at the end, oh yeah, by the way, Sn2 and E2 compete with each other under certain circumstances, you're not going to be like, whoa, I never saw that coming. Why do I have to, now I have to memorize that? Hopefully this will get built into your understanding of the structure and reactivity of these organic molecules. All right. So a second issue we want to talk about, because you'll recall we got into all of this just talking about the concerted reaction. Last time we were proposing experiments that would demonstrate whether it was front side versus back side attack. And we had proposed experiments that would tell us whether it was concerted or stepwise. I want to talk about this stepwise alternative now with its energy diagram. Let's see. And I want to talk about these are multiple steps, and so we can consider HOMO and LUMO in each one. So let's talk about this first step. As I told you in the first step of this stepwise mechanism, which we're calling SN1, first the carbon iodide bond breaks, and then you make the new bond. And maybe I'll give you an actual example. We'll use the same molecule, but as our nucleophile, we're going to use methanol. which is actually a solvent, and it's also a pretty weak nucleophile. It's also a pretty weak base. We'll talk about how you can tell that. But when your nucleophile is really weak, it is not reactive enough to attack first. It has to wait for the leaving group to leave. Now, we've talked about all sorts of reactions as being HOMO attacks LUMO, but the first step of this reaction just has one arrow, only one thing's happening, and it's the leaving group is leaving, so nothing's attacking anything. And this step is difficult, I think, for some people to justify. What? Iodide just decides it's bored and leaves? Is that what happens? And the answer to that is sort of, but not quite. Let's look at our gallery of molecules. I don't know. Can I find alkyl halide? Nope. BRO. Nope. CLOR. Close enough. So you know that in our simulated molecules we have bond vibrations. Bonds are sort of springs, and we have bond angle vibrations. We also have molecules tumbling into each other rapidly, though we're not getting that because this is just one simulated molecule. But if we speed up the simulation and turn up the temperature, you can see what's going on here. And do you see how much those bonds are varying from their equilibrium distance? Okay. So the bonds between the carbon and its substituents are dynamic. And one way we can represent that would be to think, hesitate to do this, why not? To think of the bond as a spring, and iodide is going back and forth, boingy, boingy. I can't spell boingy. The whole time. If you were to plot this with here, carbon, iodide distance, and energy here, and maybe you've seen something like this in your general chemistry classes. There's some equilibrium distance where you get a minimum in energy, and if you get too close, you start to get electrostatic repulsion. But if you get too far away, you lose the energy of bonding, and you go back up to the sort of non-bonded energy level that's sort of just here. And that goes on and on out to infinite distance. So the process of going boingy, boingy, boingy back and forth is if we were to represent our molecule as a little ball rolling along this surface. That's the vibration. We change the distance, but then we go too high in energy, so we come back. Now, what would happen if I add enough kinetic energy for this ball to get up here? If it goes far enough away, then it's just gone. There's no, and the slope of the energy landscape doesn't change very much, so it's gone and it's not coming back. Now, if it gets all the way up here, and then it slides back, and then it gets all the way up here, and then maybe back. But it's like it's on a swing, and it's getting ever higher and higher and higher and higher, and then you jump out of the swing, and then you break your arm. No, didn't actually happen to me, but I'm always a little bit. I like to swing, but I'm always scared to jump out of it. Okay, so the process of the leaving group leaving looks like the molecule getting enough kinetic energy that we can stretch to higher carbon iodide distance, And if we get far enough out, the spring snaps, there's no bond anymore, and the group is free. So you can see that's going to depend on time and probability, right? If we don't have a lot of kinetic energy, then there's some probability that just out of the blue, our system might swing all the way over here, and the leaving group could leave, but that'll be pretty rare, which means the reaction's slow. And what gives an individual molecule the kinetic energy for this to happen? Well, it's probably these molecules bumping into each other and other solvent molecules that give you enough internal vibration energy that you can break the bond. But again, the process is slow. Right? Does that sort of give you a sense for what's going on here? Because when we draw the arrow, we're not going to show any of that. We're just going to show iodide left. But you'll know now why it happens, because it just happened to have enough kinetic energy to leave. And what's left behind, once iodide is clear out here on the curve at infinite distance, is this carbocation. All right. Any questions you want to ask about that first step? Yeah.
That must be a slow step.
Yes. That is the slow step. It's low probability. Because of that, the transition state is high in energy. And the intermediate is also high in energy because you've broken a bond. Okay? One interesting thing that we'll talk about, it's called the Hammond Postulate, but it basically says that on an energy diagram, two adjacent states that are close in energy must also be close in geometry. And we will see that transition state A is much closer in energy to the intermediate than it is to the starting material. And what that tells you is that transition state A is very much like a carbocation. In other words, this transition state has the carbon iodide bond mostly gone, and the positive charge mostly on the carbon. And so you would predict that if we could, the trouble is we can't observe transition states, we can observe intermediates. So if we can learn about what makes an intermediate here more or less stable, we can then learn by inference what makes transition state A more or less stable, and that in turn will tell us how fast or slow we should expect the reaction to be. So you're going to read about the Hammond Postulate, and you should read what the text says on it, but it doesn't need to be any more complicated than this. Two states in an energy diagram that are adjacent to each other and are close in energy must also be close in geometry. So the transition state will resemble more whatever starting material or product or intermediate to which it is closest, adjacent starting material, product, or intermediate to which it is closest in energy. All right, so let's talk about intermediate stability. Let's talk about what makes a carbocation stable. And this is the result of tons and tons of research. People have observed carbocations before, and I will summarize what their findings are, and then I will describe for you why they are that way. So in terms of stability, what I'm showing you here is a methyl carbocation. I'm not sure if I've ever said this to you guys. When I was here as a student, I think I had already taken 351 and 352. I can't remember. I was in on a Saturday for some reason in the tutorial lab, and I heard these two guys trying to help each other with OChem homework. And I think bless their hearts is what we say in the South when we're about to make fun of people, but we don't want to act like we're making fun of people. Is that true? Yeah. In any case, they were explaining something about carbocations, except they called it a carbocation, which you now know, right? I mean, you wouldn't necessarily know that, but yes, it is pronounced carbocation. If you want to tick off chemists, you say, what about that carbocation? And then they might respond by saying, have a good summer vacation. So anyway, yeah, I will abbreviate carbocation as a C with a plus by it. This is methyl carbocation. This is a primary carbocation. That's because the positive charge is on a primary carbon. This is a secondary carbocation where the positive charge is on a secondary carbon. And then here is a tertiary carbocation with the positive charge on a tertiary carbon. And stability tracks with increasing number of alkyl groups on the carbocation. So I'm going to introduce a term that we're going to use a lot, increasing substitution. What we mean by that is we're substituting out alkyl groups. We're substituting out protons for alkyl groups, or putting in alkyl groups for protons. So whenever you hear somebody say, oh, this carbocation is more substituted than this one, they just mean it has more alkyl groups, right? That's the lingo. Don't get confused between that use of the term substituted and substitution versus the reaction substitution. I realize that's confusing, and the reason it's that way is because we discover these kinds of things haphazardly here and there and not in a linear fashion, and so we just bump up against stuff when it comes to how we talk about chemistry. Okay, so increasing substitution, and also in this direction is increasing stability. So tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl. And by stability, I think we should probably just say relative stability, because the tertiary carbocation is still pretty unstable. It's just that the secondary carbocation is more unstable. The primary carbocation is even more unstable. And the primary carbocation is even more than that unstable. The other thing I will say is that these stability trends really apply to molecules in solution. If you're in the gas phase, the rules change. Fortunately, we don't have a lot of day-to-day experience in biology and in nature with gas phase kinds of reactions. So unless you intend to do a lot of mass spectrometry where you're doing things in a high vacuum, or unless you want to study the composition of interstellar space and what molecules are out there, these trends will hold. Okay? Now, you can memorize that. Go ahead.
Is the increasing relative stability just because there's more molecules to share that charge?
Is the increasing stability just because there's more, I would say, atoms around to share the charge? Yes. Yeah. The explanation for that, you can think about two different things. First, let's notice the structure of the carbocations. What is the hybridization of that carbon, the positively charged carbon, in each case? Yeah, the positively charged carbon is Sp2, and therefore geometry about that carbon must be trigonal planar, and each carbocation has an empty p orbital, which is the LUMO, right? And all of these carbon-carbon and carbon-hydrogen bonds are in the plane of the page. If we were to draw this empty p orbital on one of these, it would look as if all of these carbon-hydrogen bonds are in the plane of the page. One lobe of the p orbital would be coming out towards us, and another lobe would be going back into the page away from us. Now, there's two different reasons why. The first has to do with the fact that sp3 carbons are less electronegative than sp2 carbons. And the reason for that is because orbitals with more s character hold their electrons closer and tighter to the nucleus, and that is where we get electronegativity from. What this means is sp3 hybridized carbons are electron rich relative to sp2, and so the more of these sp3 carbons you have, the more opportunities you have for inductive donation of electron density from the neighboring carbons. In other words, the sp3 carbon can be stabilized, or sorry, the sp2 carbon can be stabilized somewhat by electron donation, inductive electron donation from these alkyl groups. Now, you've heard of inductive electron withdrawal, which was how we rationalized why trifluoroacetic acid was more acidic than just regular acetic acid. The reason is these nearby carbon-fluorine bonds were pulling electron density away from the carbon, which was in turn pulling electron density away from the next carbon, which was in turn pulling electron density away from the oxygen. Same thing here, only it's donation of electron density instead of withdrawing of electron density. Okay. Second principle is, for the second time today, hyperconjugation. Dun, dun, dun. In fact, I have to be careful asking questions about why on the exam, because if the word hyperconjugation is in the answer, and it is often in the right answer when the question is why, the question just becomes easy because all you have to know is hyperconjugation is the answer to everything, which it isn't, but we're going to use it in this case. All right, so let's draw one of these carbocations, and let's just choose the primary carbocation to begin with, and let's draw it as though we are looking at it from the side. So there's going to be a hydrogen here, and then a methyl group here. And I'm going to draw this empty p orbital that's on the positively charged carbon. And at this stage, this should start to look eerily familiar. In fact, maybe we'll just go full-on familiar by using the colors we used for hyperconjugation earlier. This is the empty p orbital, the LUMO, but on an adjacent carbon and lined up with that empty p orbital, you have a filled carbon-hydrogen bond. We'll still call this a beta carbon. We'll call the carbon with the positive charge the alpha carbon. And you've got a filled sigma bonding orbital here, and it is adjacent to and lined up with the sigma star, and, or I'm sorry, the empty p orbital. All right. It's very much like what we did before with hyperconjugation in the alkyl halide, only the empty orbital in this case is the p orbital and instead of the sigma star. But the same principles apply. The hyperconjugation allows the electrons in the filled orbital to spread out toward the alpha carbon, and it allows the LUMO to spread out toward the beta hydrogen. And if you want, I mean, if we were to draw what the actual LUMO looked like, if you did a calculation, Spartan doesn't do carbocations, so I can't do that for you right here. It's pretty trivial to do the calculations. I just don't have the results handy, and so it's just easier to draw them this way. But what you would see for the LUMO of this molecule would be it looks mostly like a p orbital on the positively charged carbon, but there's some of it on the adjacent hydrogen. Right. And I guess if we were to, I just want to emphasize this point that in order for hyperconjugation to occur, sigma to p hyperconjugation, the filled orbital has to be able to line up with the empty orbital. So if we were to look from the side at this molecule, look down the methyl group, and then the carbon in the back is the carbocation that's trigonal planar. The empty p orbital from that carbon would be here, and then the filled carbon-hydrogen orbital would be there. So what you're looking for is overlap of the sigma with the p. And, oops, that's not even real. Okay, so they have to line up. And one thing you actually see if you were to do the math is that these other carbon-hydrogen bonds can overlap somewhat with the p, with this down lobe of the p orbital. They're not quite as well lined up, but they're not perpendicular either. And so you can, if you did the calculations, and again, this isn't that important, you would see a little bit of LUMO on the other hydrogens too. The p orbital is a little bit different than the sigma star antibonding orbital. We're going to see later on that it's only those protons that are anti to the sigma star that can participate in hyperconjugation. Whereas for the full-on carbocation, because that p orbital is evenly spaced on above and below the plane of the carbocation, actually all of these protons have LUMO on them. The distinction there means nothing at this point. It will matter in a few days, probably Wednesday, when we talk in greater detail about elimination reactions. So you can imagine that spreading out electrons via hyperconjugation towards the positively charged carbon would be stabilizing. So it's all about delocalizing a positive charge. You can do that through the inductive effect here. Inductive electron donation by sp3 hybridized carbons to more electronegative sp2 carbons. And then also occurring at the same time, and perhaps even related, you've got sigma to p hyperconjugation. And of course, if you look, the more alkyl groups you have on your carbocation, the more adjacent CH bonds you have to do this. So these are the reasons why more substituted carbons are more substituted carbocations are more stable than less substituted carbocations. And we'll see in this class that in terms of intermediates for the Sn1 reaction, this tertiary carbocation is an okay intermediate. The secondary carbocation is okay, but less so. And the primary carbocation in solution is generally not observed. And then the methyl carbocation in solution, it's, are you kidding me? All right, gas phase totally changes, but okay. So now let's make a hypothesis about the rate of the Sn1 reaction, remembering that the intermediate stability is related to transition state stability. So let's compare the rate of the Sn1 reaction, by which we also mean the height of the transition state in energy for the following alkyl halides. Let's do primary, secondary, tertiary. All right. So let's put them in order of fastness of Sn2. All right. Whoops. Back up. Let's put them in order of fastness for Sn1. To do this, think about the carbocationic intermediate and its stability. Then connect that to the stability of the transition state. So what do you got? What do you think is the fastest in Sn1? Go ahead.
Would it be the first one because with all like those other carbon groups right next to them, it'd be nice and relatively stable compared to the other one.
Right. The rate of Sn1 would be fastest for the tertiary alkyl halide because its intermediate is the more stable carbocation. Okay, so that means that transition state A is lower in energy than it would be for the other. Good. And that's, again, we're connecting the stability of the carbocationic intermediate with how high up in energy the transition state is. So then next should be what?
What would an Sn1 reaction look like?
That would be the leaving group leaves. We're just doing the first step, rather. So, and the first step is the rate determining one. So that's why we're only talking about that first step, but referring to the overall rate of the reaction. What should be next for next in rate? What is the next fastest one? Go ahead.
The BR. Oh no, yeah, I did the last one.
This one?
The second one would be the 3-1.
Oh, okay.
It's hard to say what the
That's right. It is a secondary carbon. The little degree symbol just means is a way I think they sometimes use in math of writing secondary.
Second degree.
Secondary and tertiary. Okay. If you get up to quaternary, well, I was going to give you a pronunciation guide. Tertiary, secondary, and primary are easy to pronounce. When you get to quaternary, you have two different options, and I like to switch them up just to keep people guessing. You can either go quaternary or quaternary. And
how can you get quaternary with a cation, with a carbon cation?
You can't. Yep. Can you get a quaternary carbon with a carbocation? No, you can't. Right. So the secondary alkyl halide would give you the secondary carbocation, which is less stable than the tertiary carbocation. So 1 is faster than 2, and the leaving group leaving to give you a primary carbocation not observed. So actually, there's going to be no Sn1 type reaction for primary alkyl halides because their corresponding carbocationic intermediates are too high in energy and the reaction is just too slow. So we'll say that because all of these reactions are slow, we will say that tertiary alkyl halides react slow in the Sn1 reaction, but secondary alkyl halides react even slower. Okay. All right. Yes.
So would we say then basic? Oh, we already have it observed. Just like no way ever.
What? Yeah, we're not going to draw primary carbocations as intermediates in reactions in solution. Yep. Okay, so we're beginning to develop a sense for the reactivity of the starting materials. We focused a lot on the alkyl halide today. We're going to continue that next time, and we're also going to bring in the identity of the nucleophile, and that's going to help us see which way this reaction could go. All right, have a good weekend. Good luck on the test. See you Monday.